Hello, I'm your friendly neighborhood Dr. Jake here, and today we're going to be talking all about electronics. As some of you may have noticed, I recently posted a blog about going over some of the basics of electricity and electrical circuits. I'm actually going to have a part 2 blog coming up here pretty soon, where I'm going to go into even more detail about some common circuit components. But today, you're going to get the full meal deal all in one nice big sandwich, one big electricity sandwich. So let me go ahead and show my slides here. So again, Electrifying STEM, a crash course in circuitry to help spark curiosity in your classroom. As you can see here, the image to the left there is a breadboard, and we'll be talking about those later on as well. But this image kind of gives you an idea of what kind of tinkering you can do in your classroom when it comes to inspiring your students to explore the subject of circuitry and to get excited about it and to gain a better understanding of it. And not just for the students, but for you yourself as the instructor, because after all, the more confident you are in these different STEM subjects, the more confident you can make your students, the more you can instill that confidence in your class. So, of course, my name is Dr. Jake Rourke. So I graduated at the BS in Physics and Astronomy at Purdue University in 2012. Then I graduated with an MA and a PhD in Physics from Kent State University in 2018, where I studied neutron stars. And I joined the STEM Education Works team in January of 2021 as a curriculum and outreach specialist. And I've always had a great passion for taking very complex concepts within STEM, particularly within physics. If I do say so myself, I do have a little bit of a bias towards physics. But I like to take these ideas and really break them down and make them digestible for the general public. And that especially goes for both teachers and students alike. And so the first thing that we're going to go over today is the very basics of electricity and electrical circuits. We're going to start off with the easy stuff and then work our way into some of the harder stuff later on. So right off the bat, what is electricity? So electricity can be defined as a form of energy that is created by the flow of electrons along a certain path, i.e. an electrical circuit. So for instance, lightning is an example of electricity. It's a situation where you have charges that are being exchanged between the ground and the atmosphere, and then that's going to build up an electric charge difference between the atmosphere and the ground, and all of a sudden you get a discharge and that lightning strike comes down and it alleviates the differences between the positive and negative charges between the ground and the clouds. We're going to keep things a little bit more simple than that and more safe than that today when we take a look at some of the tools that we can use to implement circuitry in your classroom. So at the end of the day, all matter has electrons in it, at least the type of matter that we're typically used to interacting with. So electrons are inherently part of all the matter around us that we normally interact with. And if you take a look at the little image to the lower right on the slide there, you'll see a very, very basic model of an atom. Of course, you have your neutrons and your protons sitting at the nucleus of the atom in the center, and you have the electrons whizzing around on the outside. And the fact that those electrons aren't really physically attached to the nucleus, the fact that they're simply bound in these potential states allows electrons to hop from one atom to another. And that, at the end of the day, is the basis of electricity, how electrons can flow through certain materials. And speaking of certain materials, there are some materials out there that allow electricity to flow through them very easily. We call those conductors. And in terms of objects, materials that don't allow electricity to flow through them very easily, think of things like plastic or wood. We call those insulators. And so, of course, when we're taking a look at electrical circuits, one of the things to keep in mind is some of the common components that we see in an electrical circuit. So here in the middle of your screen, we can see a fairly simple version of an electrical circuit. Of course, we have our battery there in the back that is serving as our power source. Then we have our load, which is like our light bulb, as we can see here. So a load is basically defined as any device that takes in electricity and outputs it in some other form, like light, sound, vibration, what have you. And then, of course, we have wire. That's an important part of any electronic circuit. And you can additionally add in a switch there. And notice what the switch is doing is the switch allows you to take this nice continuous round path that we see here, and it allows us to break that path. So in the image up to the right here, we see a racetrack. And I think a racetrack is a really great analogy for teaching students the basics of electrical circuits, because the concept behind an electrical circuit, the main idea behind it is that you have to have a closed loop. If you don't, if you were to open that switch that we see in the middle of our screen there, then what would happen? Well, the circuit would no longer be complete. You'd have a broken circuit. And in order for the electrons in a circuit to feel the full potential, the full force of the battery, of the power source in our circuit, it needs to be connected on both sides in order for those electrons to flow. So in the case of the racetrack, in the upper right portion of the screen there, imagine that a big tree falls down and it blocks the way for the cars to go. And in that case, the cars aren't going to move anywhere anymore because they're being blocked and they can't go in that continuous circular motion. So pretty basic stuff. When it comes to what's actually happening inside of an electrical circuit, this is kind of a crude model of what's going on inside of the wires of a circuit. So again, the wires are there simply to allow us to form this nice continuous path that will allow the flow of electricity. And this will allow the electrons in your wires and your other circuit components to feel the full influence of your power source in your circuit. And as we can see here, if we look up close, basically you can imagine these electrons being traded between atoms along the path of your circuit. Now, one thing to keep in mind when it comes to circuitry, when we talk about the direction of current in a circuit, then we're talking actually about the movement of the electrons, but in the opposite direction. So what that means is when we refer to the direction of current in a circuit, we will have it go this way, but the electrons, in fact, are going the opposite way. So why is that? That's pretty confusing, right? Well, you can thank Benjamin Franklin down there in the bottom left corner, Benny G, as I like to call him. Benjamin Franklin wearing his sunglasses, saying deal with it. When Benjamin Franklin was first fidgeting around with electrical circuits and doing experiments and discovering some of the early laws of electricity, he decided that he presumed that electrons, the things that are actually moving in your circuit, were positively charged. And so that is why today the actual direction of conventional current and the direction of the electron flow in a circuit are actually opposites. They're in opposite directions. So whether it's daylight savings time or the direction of conventional current, you can blame it on Benjamin Franklin. And of course, when we get into talking about circuits, there's also topics like, for instance, DC current versus AC current. When we plug things into our walls at home, we are inevitably always using AC current. AC current is a lot easier to send over long distances. The outlets in our houses are based off of that. But if I were to take a battery, a simple battery, let's say a 9-volt battery, and hook it up to some wire and maybe a light bulb, that would be direct current. When it comes to teaching these ideas in circuitry to your class, it's always a good idea to start off with direct current. And in fact, for a vast majority of your lessons, you're probably going to stick with direct current. AC current introduces a lot of mathematical complexities to it. And just to keep things simple, having a nice constant voltage that, as you see over on the left side of the screen there, as opposed to a voltage that goes from positive through 0 down to negative, back and forth, back and forth. You can see how that can get kind of confusing to younger students. So sticking with DC current is typically advised especially for younger students. And so, of course, we also have to talk a little bit about series circuits versus parallel circuits. So the concept behind this is fairly simple to understand. So imagine that you have a line that you're going through to get on a roller coaster, okay? You're at an amusement park and there's only one line. Well, in that situation, that would represent a series type circuit. It'd be a good representation of it because as you can see in the series type circuit, there's really only one path that the electrons can flow through. So the electrons are going to start at the top of the battery there. They're going to start flowing through the circuit. They're going to flow through the first light bulb, the second light bulb, and the third light bulb. And as you can guess, because all of those circuit components are all on a single loop, they share a common path. So in that situation, the current would be constant throughout that entire circuit. Because after all, you can think about current as a bunch of cars driving around. Maybe if you ever go through a section of the interstate where you have that big loop around a central city. I go around, what is it, I-65, I-675 around Indy all the time. So you can think about it where the electrons in your circuit are like cars driving on a road. They all have to pretty much go the same speed if they're all on the same path. And so in the situation with the series circuit, over to the left side of the screen, you'll notice that because the current is constant, that means that the voltage drops across each of those light bulbs are going to be different. Now, for the sake of simplicity, let's assume that these light bulbs are all identical. Let's say we have a 12-volt battery that's in that circuit. What that means is as the electricity moves through one light bulb, the other one, and the third one, there's going to be a certain voltage drop across that load device. And so if all of these light bulbs are identical and they have the same amount of resistance, then you could say that the voltage drop across the first light bulb would be 4 volts, and then 12, I'm sorry, let me say that again. It's going to be, it's going to be 4 and then 8 and then 12. And so that's going to add up to the total voltage that we're getting from our battery. And in this case, we would have like a 12-volt battery. Now, in the case of a parallel circuit, it's wired a little differently. Now we have multiple paths the electrons can take. And what's really nice about this is if one of our light bulbs burns out, it means that the rest of them don't burn out. So during this holiday season, as we get into Halloween, Thanksgiving, and especially Christmas, this could be a very good example for you to use for your students to talk about Christmas lights. So if a Christmas light is set up in such a way that all of the lights are in series, that's not a good idea because after all, if one of those lights burns out, then one moment. If one of those lights burns out, then all of the lights are actually going to go out. So in the case of a parallel circuit, you'll notice that if one light burns out, then the rest of them are still going to shine bright. And that's exactly how Christmas lights are engineered. In fact, all of the lights in our houses are engineered in such a way that the circuits are in parallel. So after all, you don't want your toaster to not work if the light in your living room burns out. And in the case of the parallel circuit, instead of in the series circuit, we had a constant current going through all of those light bulbs, and we had maybe differing voltages depending on if they were the same light bulb or they were different. In the case of the parallel circuit, we have the exact opposite. We have constant voltage being delivered to all of them equally, but different current depending on what device is in each branch of that path. Now, I've talked a little bit about these words like voltage, current, and resistance, and let's jump into these concepts and explore them in a little bit more detail. So I really like this image. This is a terrific image to use for teaching your students how voltage, current, and resistance work together. And later on, we're going to talk about how they relate to each other via Ohm's law. But basically, you can see here, you can think of current as what's the speed with which the electrons are moving through your circuit. The voltage is kind of the thing pushing those electrons through your circuit. And up there up top, the guy with the cowboy hat that says ohm on it, that's going to represent resistance. And that resistance is going to try to resist the flow of electricity through the wires and components of your circuit. And so right off the bat, let's talk about voltage. This one's probably the easiest concept to understand. You can think of voltage as being the amount of driving force that pushes or pulls electrons through a circuit. So in that sense, it's kind of like a pump in the sense that, you know, the faster we're pumping a water pump, the more rapidly we're going to get water to flow out of it. This value, voltage, is measured, of course, in volts. That is, we use the capital letter V for that unit. And ultimately, the voltage in a circuit is determined by the power source we're using in our circuit. So if I have a 9-volt battery hooked up to some wires and some light bulbs, then the total amount of voltage in my circuit is 12 volts. Again, when in doubt, if you want to know what the voltage is that you're working with, just look at your power source that you're using. You may also have a situation where you have an electric voltage and current generator. So if you have that set up for your current, you can actually take a knob and change how much voltage is being applied to your current. So voltage in this case, of course, is like the figure in this little cartoon. That is the pushing force that is pushing electrons through your circuit. Now, resistance, judging by the name, it should be pretty obvious what that is to begin with. It is the level at which a circuit resists the flow of electricity. This value is measured in ohms, and it's given by that Greek letter omega there. And it's ultimately determined by the load devices and the resistors that we use in our circuit. We'll talk a little bit more about resistors here later on, but really at the end of the day, if there's any device in your circuit that is harvesting energy from your battery, then at the end of the day, it's going to have some kind of internal resistance that is characteristic of that object, of that circuit component. And then sometimes we have resistors where we just want to tweak the total resistance in our circuit so we get just the right voltage drop across an object, or maybe just the right current. And also, you can think of resistance as like the brakes on on your circuit, or possibly like a speed bump. Again, it's what is resisting the flow of electrons through your wires and other circuit components. And in our little image that we showed previously, our little guy with a cowboy hat that says ohm, that kind of represents our resistance. And again, your resistance is causing those electrons, or maybe in the analogy of the race car, you're the race cars that are going around the track. It is causing those electrons or those cars around the racetrack to slow down and have to move at a slower speed. And of course, lastly, we come to current. And this is ultimately the speed at which electrons are flowing through your circuit. So again, you can kind of think about it like the speed at which cars are going around a racetrack. And again, if you have a simple series circuit, all those cars have to be moving at the same speed, or you get a pile up. So all electrons are basically feeling the same amount of force no matter where they are on the circuit from the power source that you're using. And of course, this value is measured in amperes, named after the guy who discovered current and coined it, or we call them amps for short. We write that as a capital A. Now, current is interesting because in the case of voltage, we can just look at the power source we're using in our circuit, and we could say, bam, the voltage that's being applied to this circuit is 12 volts, or 3 volts, or 4 volts. And in the case of the resistance in a circuit, we'll show you some equations here later on to help you calculate total resistance in a circuit. But again, that's just a matter of, okay, what are the load devices that I'm using, like let's say a light bulb, and what are the resistors that I'm using in a circuit? And you just add them up according to if it's a series or a parallel circuit. and you get your total value. But current is a little different. You can think of current as almost being like a secondary value to a circuit. Current kind of pops out given whatever voltage and whatever resistance you are using in your circuit. So in that sense, it's less fundamental to the circuit components that you're actually using in your circuit. And as we can see here, we get a little sneak peek of Ohm's law to the lower right portion of the screen there, talking about how we define current with voltage and resistance. And again, our current measured in amps is represented by this little guy who's tied up, being pushed through this tube by voltage, but being resisted by the resistance in our circuit. Which brings us to Ohm's law. There are so many laws in, if you dig into the complexities of circuitry, even if you go on to take some classes in college, if you go on to be an electrical engineer, there are so many complex laws that go into circuit analysis that really boil down to Ohm's law. And Ohm's law basically states what you're seeing here. Your voltage in your circuit is equal to the current times the resistance, V equals IR. Very common equation that your students will be using quite frequently when they're studying circuitry in the STEM classroom. So again, V is our voltage in our circuit, I is the current going through our circuit, and R is the total resistance. Now, one thing I have to admit to you, Ohm's law isn't actually a law. It's kind of a misnomer that we call it Ohm's law, because what Ohm's law presumes is that it presumes that this value that we see, this R value resistance, is actually constant in all materials. And that's not actually the case. Even with resistors, common resistors that you'll put into a circuit, common resistors, they are specifically engineered to have a really super constant resistance. But out in nature, most objects, the resistance that they have will be dependent on things like their temperature, other sorts of things in the environment. So that means that Ohm's law really isn't a law per se. Really, you should think about Ohm's law as being rewritten as R is equal to V divided by I. In other words, Ohm's law is really actually just a definition of resistance. It's just kind of a way that we define the overall resistance in a circuit by taking the voltage in the circuit, dividing it by I, and that is equal to whatever resistance you must have in your circuit to achieve those two numbers. And when we're talking about resistance in parallel circuits versus series circuits, we do calculate them differently. In a series circuit, we basically just go through and we add up all the resistances of all of the devices that are contributing to the resistance in our circuit. So you may have a light bulb that has a certain amount of resistance to it, although typically light bulbs are made to have pretty low resistance. But let's say you have a very simple circuit with a battery and 3 resistors in series. In that case, you literally just add up the resistances together, and that is your total resistance that you're going to use to look at the entirety of your circuit. In the case of parallel circuits, it's a similar idea. You can imagine a situation where you have a battery hooked up to 3 resistors in parallel, and in that case, it's a little different. You don't add them together. Instead, 1 over the total resistance of your circuit is equal to 1 over R1 plus 1 over R2, so on and so forth until you've accounted for all the resistors in your system. And so another interesting thing about Ohm's law is that Ohm's law can be used not only to analyze an entire circuit, but it can also be used to analyze specific components of a circuit. So for instance, if I know that if I have a circuit where I have a battery and it's hooked up to a single resistor and I just have electrons going through that loop, in that case, I know what my voltage is. It's whatever voltage it says on my battery. And I have my resistance because it's given by the color codes on the resistors. If you ever need to look up, sometimes some resistors have the amount of resistance printed on them. Other times resistors will have colored bands on them. And if you just type in Google resistance color chart, it'll show you how to read off the resistance values. Of course, I always have issues with that because I'm colorblind, so sometimes I can't tell the colors of the stripes, and that's where multimeters come in handy and can help you get the exact value of your resistance. But anyways, in that situation, you can calculate the current that's going through your circuit, your full circuit, with just a battery and a resistor. But let's say that you're specifically looking at one single resistor inside of your circuit. If we know the total voltage drop across that resistor, and we know what the resistance of that particular resistor is, we can tell the exact amount of current flowing through that part of the circuit. So not only can Ohm's law be applied on the large scale for an entire circuit, but can also be applied to specific certain components. So you can, depending on what you're interested in your circuit, you may have the full circuit you're looking at, or just a small component of it that you can use Ohm's law to analyze. So, as I mentioned before, the process of using Ohm's law is pretty simple. Again, we're going to go with the things that are most easily recognizable. So V is a pretty easy recognizable thing. It's going to be the voltage of your battery. Let's say it's 9 volts. Then we can go and calculate our total resistance in our circuit. Let's say in this case, the total resistance is 100 ohms. And then from there, we can use that, and we can use Ohm's law to determine what the current is going through our circuit. And so we take 9 volts divided by 100 ohms, and we get 0.09 amps. So when it comes to going through these examples of Ohm's law, it's always a good idea just to go through and do some practice problems. But not only is it important for both you and your students to go through and do some practice and whatnot, but you can also have your students do this theoretically on paper. So write out, given a certain resistance, given a certain voltage, for instance, what would my current be? Or you could have your students actually build it in class, which is why circuitry is such a powerful tool for STEM education, because it really gives students a good idea of how theory mixes in with experiment and how they can discover the same things using these two different approaches. And now we'll talk a little bit about some common circuit components. In this section, I'll demystify what some of these things that you saw earlier on in our presentation, like in this image right here. What are all these wires there? What are those cylindrical objects? What are the little skinny things sticking up? We'll talk about some of the most common circuit components now. Okay, so among the most common circuit components that you'll find capacitors, resistors, inductors, transistors, even microchips, and diodes. And we're going to be going over each of those in this section. So when it comes to common circuit components, probably the most common basic thing that you could put into a circuit is a resistor. And as you can see here on the image there, it's a little like cylindrical object. Sometimes it's kind of rounded, so it kind of has a hot dog shape. And it has those colored lines on it to tell you what the resistance of that resistor should be. And so you could kind of think of resistors as being like the speed bumps in your circuit. After all, they're called resistors, so they resist electric flow, and they're going to force those electrons to slow down in your circuit and move through your wiring and circuit components at a lower pace. And next up, we have diodes. Diodes are a little bit more complex because basically what a diode does is it only allows current to flow through in one direction in the part of the circuit where you insert it. So you can think about it like a one-way street. And if any of you are wondering if you've ever worked with diodes before, there's a very good chance you have, because over on the bottom right portion of the screen there, we see a little image of an LED. And for those who don't already know, the acronym LED stands for light emitting diode. So it itself is a diode. In other words, anything that is a diode only allows electricity to pass through in one direction, but not the other. There's a lot of really complex things you can do with diodes in a circuit, especially as your students move up to higher grades in high school and in college. We don't have enough time to go into that today, but there are some pretty complex things you can do, like, for instance, turning AC current into DC current with a set of diodes. And we'll look at these LEDs a little bit more here coming up soon when we take a look at one of the components of the examples that we're going to show here later on of how to insert circuitry into your STEM classroom. Now, the next two most complex objects that you can put into a circuit would be transistors and potentiometers. And these two things are pretty closely related. First off, we have transistors. And you can think of a transistor as being like the gate of a castle. It's either open or it's closed. It's basically a circuit component that you can put into a circuit, and particularly in the case of breadboards. And what you can do is you can allow electricity to flow through it or disallow electricity to flow through it. So it's a way of allowing or disallowing current to flow given certain conditions, or given certain timing aspects if you are programming your circuit with something like a microbit. We'll talk about transistors a little more here later on. A potentiometer is kind of similar to a transistor. You can kind of think of a potentiometer as like a hybrid between a resistor and a transistor, because sometimes potentiometers are referred to as variable resistors. The idea of a potentiometer is kind of like that of a transistor, in the sense that instead of the gate being either opened or closed, the gate can be open, closed, or anything in between. And that's why you'll often see these continuous dials that are built into potentiometers that you might include in a circuit. So it's more complex than a transistor because it has more than one state. And it's kind of like a resistor in the sense that as you turn it, as you're closing off the amount of current that's passing through it, it's acting like a really, really tough resistor with a really high resistance. But then as you turn it the other way, it acts like that resistance kind of disappears. And lastly, some of the more complex circuit components that you could use in your classroom when you're teaching circuitry are capacitors and inductors. So a capacitor, you kind of want to think of it like a dam, like the picture we have over here in the upper right of our slide there. A dam, if you think about it, is basically an object that allows us to have a bunch of water over here and no water over here. So we get a big difference between the water down here at the bottom and the water up here at the top. There's a big difference in how much potential energy the water between the section of the dam is. The water that's way high up on the side of the dam that is holding back water, that's going to have a really high potential energy. Whereas the one down here is going to have a really low potential energy because that water's closer to the surface of the earth. Well, in the case of a capacitor allows you to basically build up positive charge on one end and negative charge on the other end. And there's a lot of really interesting things you can do with capacitors in terms of circuitry in your classroom, especially if you eventually make it up to alternating currents. There's some cool math you can do. It's a good way of teaching pre-calc and calculus to students. And lastly, we have inductors. Now, I really couldn't come up with any other image for this except for Magneto from the X-Men, you know. Basically what an inductor is, it's a coil of wire. And that's really, at the end of the day, all it is. But what's interesting about it is as you allow current to flow through that coil of wire, when electrons go around in a circle like that, they generate a magnetic field. And due to a little thing called Faraday's law, what that inductor is going to do is it's going to create a magnetic field that resists the initial flow of electrons through it. So in a way, an inductor acts like a more complicated version of a resistor. Just like a resistor, it's going to slow down the flow of electrons through your circuit, but in a bit more of a complicated way. And again, inductors are especially interesting once you dive into things like alternating current in your classroom. Now, a little bit of a tangent about resistors. So, I'm sorry, not resistors, transistors. Transistors are kind of a big deal. And what I mean by that is this. Way back in the day when people were building early computers, they used these things called vacuum tubes. And they were these glass tubes that were, all the air was sucked out of them. And you had like a metal probe here and a metal probe here. And they would allow current to flow through at certain times and disallow current to flow through at other times. They were big and bulky, but near the middle of the 20th century, we developed these little tools called transistors. And transistors have totally been the thing that has shaped computer technology over the past 50, 60, 70 years. Transistors, what's really cool about them is that they don't have any moving parts. They are purely designed using solid state engineering, as we can see in this little diagram right here. And every transistor ultimately has three of these little prongs sticking out of it, so three little leads. One of them is referred to as the drain, one of them is referred to as the source, and one is referred to as the gate. And basically, the idea behind this is one of those, for instance, we have the drain there. That's where electrons will enter into your transistor. And the source is where they're going to leave your transistor. But by applying a voltage through a wire that's connected to that gate lead, you can control if the transistor allows electrons to flow through it or not allow electrons to flow through it. And again, that has revolutionized computer technology, not only because it has no moving parts and it's very robust and it's a very reliable technology, but you can make these transistors really, really, really tiny, like we see over in this image over to the right of our slide here. That right there, that's a microscopic image. So the transistor that we see up top there with that black box with the three wires coming off of it, that's the kind of transistor you're going to see if you are doing an experiment with a breadboard. Now, you're not going to find those type of transistors in your computer. The ones inside your computer for work or home, those are going to be microscopic. And since the development of transistors back in the day, we have been able to fit billions and billions of these things on a single microchip. And now let's talk a little bit about breadboards. Breadboards are quite literally the bread and butter of teaching circuitry in your classroom. They're a little complex to get a hang of at first, but once you get the general rules behind them, they become a really a very valuable tool for teaching circuitry. So right off the bat, this right here, this is Tony Cowabunga. Tony Cowabunga, he was really influential in breadboarding way back in the beginning. Back in like the early 80s. I mean, he figured out, I think he pretty much usually wrote on sourdough, I'm pretty sure. I think that was his trick, really. This is Chelsea All-You-Can-Eat Breadsticks Johnson. She came onto the breadboard scene a little later, in like the mid-90s. But she really, like, so many of the moves that you see nowadays in these breadboard competitions, she did it first, you know. In case you were wondering, I was just kidding. These are not what actual breadboards are, but like, that's pretty cool, huh? Like, if you could surf on a piece of bread, that'd be pretty cool. No, in fact, breadboards are not used for extreme sports. Breadboards are a very useful tool for teaching electronics and circuitry in the classroom. So you might be asking, well, they're called breadboards, so why are they called that? Well, it's because back before we had these little white slabs that you see there in the middle of the slide, up in the upper right, what people would do back in the day before we had these mass-produced breadboards that we have today, they would literally take nails, nail them into a piece of wood that would be used for cutting bread, And those nails nailed into that wood would act as nodes around which you can wrap wire and other circuit components to prototype circuits. So voila, it's called a breadboard because it was usually made out of a piece of bread used for cutting board. And at the end of the day, a breadboard, when you're looking at it, it can be a little slightly confusing. But really, at the end of the day, the only thing you need to remember is that a breadboard is typically split up into 4 different sections. As we can see here in this image, we have a section way over to the left side. That right there, that long skinny section outlined in red. And then we have 2 sections in the middle. And then lastly, we have a section on the very end on the right. The sections on the very far left and very far right, those are power strips. And those are strips where we can plug in power sources into our breadboard. And that allows us to supply the middle sections of our breadboard with a certain amount of power in our circuit. Why do we have 2 of them? Well, it's just in case if you are building a circuit that's rather complex, you may actually need 2 different sources of voltage in your circuit. Let's say a certain part of your circuit requires 3 volts of energy to run it, and maybe another part of your circuit requires 6 volts. So by having 2 different power strips, you can use 2 different levels of voltage at the same time when you're prototyping your devices. And in the middle sections here, we have our main wiring regions. That's where most of the magic is happening when we are actually building our circuits. And do keep in mind that there is a valley right in the middle of that breadboard that splits the 2 parts in the middle apart from each other. Now, right away, you might be thinking, Jake, what's up with all these holes and which ones do I use? And you look at this thing and you become very confused very quickly, but never worry. You just have to remember 2 basic rules when it comes to breadboards. So as you can see in the image over to the left there, we have a zoomed in view where we're taking a look at the holes in our power strip and in one of our middle sections. And you'll notice that the way a breadboard works is in the power strips, all of those holes that are in the same column are all connected. And in the middle sections, all of the holes that are in the same row are connected. And so you can see that very clearly if you were to take off the adhesive that is often put on the back of a breadboard that allows you to kind of stick it to a surface. I would not advise you to try to take off the adhesive because then it gets messy. These little clips can come out. But I did this for you. And in the image over to the right, you can see how along the power strips, the strips are going vertically. And in the 2 center sections, they're going horizontally. So as long as you remember that, for instance, you could give your students this little image right here is a quick little cheat sheet. It shows how all of the holes on the sides are connected vertically. The holes in the middle are connected horizontally. And once you and your students get that down, you're good to go and you're off to experiment with a breadboard. There are many different types of breadboards out there. We have full breadboards that are extra long. Most of the breadboards that we work with our kids here at STEM Education Works are half breadboards that you see in the middle there. And then we also have mini breadboards that don't feature power strips. When it comes to using breadboards, here's a perfect example of a kind of project you can do with your breadboards that specifically features our very own EV microcart from our Build Smart EV microcart curriculum. In that curriculum, your students get the chance to program their own headlights and taillights. That's what we're taking a look at over on the left side of the slide there. And on the right side of the slide, we're actually outfitting it with a variable speed motor. So you can also see on the breadboards that they're kind of organized in such a way where you have letters going across the top of it and numbers going down the side. So identifying which hole you should insert a certain component into is as simple as playing Battleship. So, C2 or B4 is just the basic way that we go about identifying which holes to insert our wires or circuit components into. And here's the actual physical version of our EV microcart here, which shows some breadboard work that we've done. It includes a transistor, a little resistor hiding in there, a potentiometer. So it's a really great way for students, even younger students, to dip their toes into the lake of circuitry and electronics. And lastly, we'll talk a little bit about multimeters. So multimeters can be your best friend in terms of determining values like voltage, current, and resistance in your circuit. So we went over Ohm's law previously. We talked about how you can calculate those values given your knowns and your unknowns in your system. But the more experimental way of doing it is using one of these guys right here. This is a handy dandy little multimeter. They're a little complex to learn how they work early on. But basically the idea is you just have to turn this dial to the right setting. You have to make sure your cords are plugged into the right ports. And from there, you can measure those very common circuit values like voltage, current, and resistance. We can see a good example of one right here. And so in conclusion today, there's a lot of great things that you can do with circuitry in your classroom. As I mentioned before, I think one of the magical things about circuitry in the STEM classroom is that you can have your students approach it from an experimental side, where they're actually building circuits with their hands and using multimeters to measure values, or you can have them come at it from a theoretical side, where they're writing down equations, writing down their knowns and unknowns, and practicing some of their math skills. Not only is tinkering and math an important part of circuitry, but there's a lot of different ways that you can incorporate other subjects into your circuitry lessons. So for instance, as I mentioned here, at the top of our slide here, we have our Build Smart EV microcart, a great way of incorporating not just electrical circuits into your classroom, but also some block coding that controls what those circuits do. Similarly, for younger students in particular, we have Brown Dog Gadgets. These are cool little crafting kits where it shows the students how to build very simple circuits. Here we have a little T-Rex guy, and he folds his arm out, and we complete the circuit. As you can see here, we have conductive tape that allows them to form that circuit and complete it, therefore lighting up the LED. So that's a great mixture of teaching. That's a great example of teaching circuitry, but also adding in some crafting and creativity to it. Horizon Educational, our products in that lineup, are also a great way to teach circuitry because they incorporate circuitry with many concepts centered around renewable energy. So in this particular case, we have a hydrogen fuel cell, and circuitry is going to be a very important part of that. Also chemistry. So bing, bang, boom, you're able to incorporate a wide range of subjects into a single lesson and truly make your STEM activities truly STEM oriented. And then lastly on our slide here, we also have Mind Labs. And Mind Labs is a very truly unique product because what it does is it mixes these concepts of circuitry in with virtual and augmented reality. So here are some blown up versions of some of the little cards. These guys will actually be probably about that size. But what you can do is you can lay these cards out on the table, and you can actually build your own circuits using the camera on an iPad. So that makes it a really cool way of introducing circuitry concepts in the realm of AR and VR. So yeah, thank you guys very much for joining me today. If you guys have any questions at all, please feel free to contact me at Jake Rourke at STEMeducationworks.com. And if you guys have any cool projects that you guys have done with circuitry in your own classrooms, please let me know. And do we have any questions at this point? Okay. Doesn't look like we have any at this point. But if you guys do have any in the near future, feel free to reach out to me and let me know. And until next time, see you guys later.